In this problem, we're using the idea of osmotic pressure to solve for the molecular mass. And a lot of the colligative property problems, molar mass is something that we do look for. So this is your osmotic pressure, which is pi. Sometimes it is a capital pi. Um, I is your Van't Hoff factor, and that's how many pieces something splits up into. Here, M is molarity, your concentration in moles per liter. I put it this way because that's how it appears on the blue sheet that you'll have. Here it is. But you have to be careful. M here means concentration. Notice it is not bold. Here, and over here where they identify the bold M, that's molar mass. But here the M is molarity, concentration. Okay, R is your R value. You can use whichever one works with your osmotic pressure. And T is temperature, and it must be in Kelvin. So, in working this particular problem, remember we're trying to solve for molar mass. And this one's talking about hemoglobin, a property in blood, and we've got 15 grams in about 100 milliliters of solution. This is about what you have in your bloodstream as a normal human being. So to get this, what we need is always know what we're looking for. Molecular mass. That is your molar mass, and it is in grams per mole. Well, they tell us how many grams we have. So again, what we're looking for here is the moles of our moles of the hemoglobin. So in order to find moles, the only thing we have here that has moles in it is molarity. So that's what we're going to solve for. So molarity, or our concentration, is going to be equal to the osmotic pressure divided by IRT. So the osmotic pressure that they tell us is in atmospheres. So molarity equals 0.0500 atmospheres divided by I. Hemoglobin is all non-metal, so it is a non-electrolyte, which means its Van't Hoff factor is 1, times my R value. I need to use the one with atmospheres, 0.0821 liter atmosphere mole K. And our temperature in Kelvin, 25 degrees C, is 298. And that should almost be pretty automatic for you. So Kelvin cancels, and then our atmospheres cancel, and our molarity is going to be in moles per liter. So in solving for this particular one, plugging everything in, I get a concentration of 0.00204 moles per liter. Now, I just want moles, so I'm going to have to work with molarity to find moles. Moles is equal to molarity times liters. So I have my molarity of 0.00204 moles per liter times my liters. They tell me I have 100 milliliters. Move it over 3 places, so times 0.1 liters. Liters cancel out, leaving me just moles, and so it is 0.00204 moles. Now I'm going to take my moles, plug that in up here, 0.000204 moles. Now I'm going to have the correct units of grams per mole, and when I get that, I end up with a molar mass of 73,400 approximately grams per mole. I went with 3 sig figs just because everything in that problem has about 3 sig figs. So now that is a huge molar mass, but hemoglobin is a big molecule. And that's how you do it with osmotic pressure.